Welcome.
Thank you so much, Jason, and thank you to the City of Calgary, Municipal Services, and the Wave Tech Center for having Qubo Consulting here to present to you on demystifying the second quantum revolution. So I am AJ Sikora. I'm the co-founder and chief learning officer of Qubo Consulting Corp. And I'm here to explain in English what this quantum revolution is all about. So, welcome to everybody. You are all welcome here at this presentation. You don't need any special physics background or anything like that. This talk is targeted to business leaders and government decision makers. So please keep an open mind. Okay, if you want to learn something new, you have to be open to it. So just don't actively fight learning today. Okay, and please ask questions. I love it when people ask questions. It lets me know that you're paying attention, that you're interested, and you understand what I'm saying. So don't be shy. Don't worry. You can interrupt me. My background is in education and business, and so I feel comfortable when there are, there's noise going on, there's people talking, hands going up, and people are excited to learn. So don't be shy. So here's a look at what we're going to talk about today. In section 1 is the introduction. So it's an introduction to possible use cases. Then I'll talk about what does quantum mean, and then we'll talk about the areas of quantum tech. In section 2, that's where we'll talk about the implications for industry. Of course, we're going to start with the quantum threat. Then we'll go into industry impacts, and then we'll talk about the opportunities and risks that are coming out of the sector. And then section 3 is global quantum investment. I like looking at these numbers to see, hey, this is a real industry. There are real dollars being invested in this, and real technologies are coming out of this industry. Okay, so then we'll look at an investment map, so a world map of who's who in the quantum, and then take action. So we give you a bunch of information. What can you do with that? We'll give you some next steps. All right, so introduction to possible quantum use cases. So we say possible quantum use cases because these are the things that could be improved with quantum technologies. Some quantum technologies are available now, but most quantum technologies are a future future solution that we could utilize. So in the energy sector, smart grids could be improved using quantum tech, and we'll look a little bit more in depth at that. Agriculture, we could have crop management to optimize the allocation of resources in order to maximize the crop yield. In travel, transportation, and logistics, we could optimize delivery routes to use less time, vehicles, drivers, and fuel. So less resources means we would save money. Okay, and then in climate change, so it could be used to improve climate models for more accurate predictions of weather events, and that is becoming increasingly more important as we notice the changing in our climate. Okay, so looking at the energy sector. So the problem is to improve smart grid management using quantum technology. So we would like to improve the production of energy, the distribution of energy, the consumption, and then of course we want to look at the security as well. So here are some possible solutions. We could use quantum sensors to improve the measurement range, resolution, and sensitivity to help detect early signs of equipment failure and monitor grid performance and integrity. Quantum simulations could be used to solve optimization problems that improve energy distribution and storage efficiency. These problems are too complicated to run on traditional or classical computers because of the huge data sets and the number of variables that go into these problems. And then smart grid communication security could be improved with quantum random number generators and quantum key distribution. If you're wondering more about those particular technologies, stay tuned for Catania's talk coming up after mine. Okay, so what does quantum mean? What comes to mind when you hear the word quantum? Just shout it out. Don't worry. Don't be shy. Yeah.
Just some level.
Some level? Yeah. Like on the tiny. Yep. Yeah. Excellent. Subatomic. Yes. Sandra, I think you said that this morning too. Yeah, right on. Dishwasher tabs. Yes. Marvel movies, dishwasher tabs, televisions, those are all quantum, right? No. There's all these businesses and other technologies that use the word quantum because it sounds cool, but it doesn't necessarily mean that they're actually using anything to do with quantum in their technologies. Except for the Marvel movies. Those ones I think are legit. Yeah. That's a joke, by the way. All right. So quantum physics, if you're wondering, is the study of the smallest particles that make up our universe. So the smallest that any matter can get. You can't break it any further. You can't split it any further. So that is the scale, the order that we're looking at. And so why could it be disruptive? Because on that level, on that order of magnitude, when we get down that small, matter behaves differently than it does in the classical world, in the macro world, here, right now, what we can see and feel and touch and smell. Okay? And these special properties that exist can be utilized to create new and improved technologies because they exhibit characteristics that we couldn't use in our classical technologies. So that means that if there's a new way to do something, that opens up opportunities and possibilities. So some of the areas of quantum technology that are being commercialized right now are quantum computing. Within quantum computing, we also have quantum optimization. There is also quantum simulation. So a simulation is, say, simulating an environment that has a number of variables and parameters to be input. If we have too many variables and parameters, we can't do it classically, so we need a quantum system to run that simulation. And so people are exploring utilizing quantum systems to simulate nature or other environments. And that can be very handy. Then there's quantum communication. Quantum communication is theoretically 100% secure. So that's an important technology. And then we look at quantum sensing as well. So quantum sensors, more precise and more sensitive. And then quantum random number generation. And as I mentioned, Catania will talk more about that one as well. Okay, so let's move on to section 2, implications for industry. This is what businesses really care about. This is what government decision makers really care about. What are the implications? So let's start off with the quantum threat. Put up your hand if you have ever heard of the quantum threat. Okay, yeah, Adam, I wanted to see your hand go up. So quantum computing is exponentially more powerful than classical computers. And it is expected that a quantum computer that is powerful enough to break encryption standards will come available in maybe 5 to 15 years. There's no set timeline. Maybe 2030, maybe. I heard somebody say Pi 2025, I think. It was like, this was a couple years ago. It was like 3 years out and they were like Pi Day and whatever, and everybody laughed. And anyways, so the general consensus is about 5 to 15 years. We don't really know. It could be sooner. As we've talked about on our panel and earlier today, the rate of acceleration of technological development is increasing. And that means that it makes it hard to predict these things about when specifically something will come online. But it's about 5 to 15 years. So if we had a quantum computer that was capable of breaking our encrypted information, we wouldn't have to worry about that until the future, right? True or false? False. True. Well, you're the quantum physicist, so Okay, so no, she's right. False. We do need to worry about it now because of this threat right here called harvest now, decrypt later. Sometimes people call it handle, HNDL, handle threat. So what that is people could steal, threat actors could steal encrypted information today. Maybe your healthcare data, maybe your banking details, I don't know, something with a long lifespan on the information. So if they stole that information today, they couldn't access it because it's encrypted. However, they're holding on to that information. They're storing it in a hard drive somewhere, in a cave. It's not connected to the internet. Okay, can't access it, right? They're saving it until they have a fault-tolerant quantum computer, until they have a quantum computing system that is capable of breaking that encryption. So that means that there is a threat today. There was a threat yesterday, actually. But I just want to make everybody aware that this is something that is going on right now. It is expected that threat actors are stealing encrypted data, they're storing it, and they're waiting until they have a computer that can break that encryption. So we'll talk a little bit more a little bit later on about what types of data they might be stealing. Okay, so let's look at this industry, data security. It follows the quantum threat nicely. So data security could be impacted because of this quantum threat. There are large implications of this because the time to prepare was yesterday. People could already have my encrypted data and they're just waiting to decrypt it in 5 or 10 years. Okay. One thing to factor in is the transition time. If you want to prepare for a post-quantum threat, then what you need is time to prepare. Because if you want to switch over a cryptographic system, it'll take you a few years to figure out which system are we going to go with, how is that going to address this threat, and then there's how much money is it going to cost? Where is the money going to come from? Then how long does it take to actually transition the technology itself? How long does it take to train your team to prepare? And how long does it take you just to find out what cryptographic assets you even had to begin with so that you can start this whole process? Sometimes that is a huge process, a few years for a large organization. That could be a number of years just to find out what assets you have that should be protected. However, there are solutions, okay? I don't want to leave you guys on a cliff here. No, there are solutions, don't worry, okay? So there are two solutions right now. So one is called post-quantum cryptography. So that's using classical systems that use more robust algorithms that are expected to be resistant against a quantum computer as well as our classical computers, okay? Now, the issue with that is we don't have the fault-tolerant quantum computer just yet, so we can't test these against an actual functional fault-tolerant quantum computer. However, we do have suggestions. All right, the US government, NIST, released 4 cryptographic algorithms, I believe it was in August, maybe it was September, I can't remember. But they recommend those algorithms to be used in post-quantum cryptography. Then the other solution, which is actually a quantum solution, is called quantum key distribution. And this is 100% theoretically secure. So I know Daniel spoke about this. So in a system like this, it's theoretically secure, but in practice, there are a number of complexities that go into the system. And the other compounding factor is humans. You're always going to have humans in the loop. The next industry we'll look at is manufacturing. So quantum could offer a couple of solutions for manufacturing. One of the most exciting ones, I think, is in new materials discovery. So if we had a quantum computer that could simulate a natural environment, we could simulate new materials. We could say, okay, I'm looking for a material that has a certain heat resistance and a certain strength or compression strength, and you could test it all in simulation before you produce it and test it in the real world. It's not going to entirely remove that R&D aspect of the development process. However, it could significantly reduce the amount of time and resources that need to be dedicated in the research and development of new materials. As well, we could look at optimization to improve operational efficiency in things like production, logistics, and supply chain. The next industry we're going to look at is healthcare. And in healthcare, there are a number of applications. So using quantum simulation, much like manufacturing with a new materials discovery, we could look at new drug discovery in the healthcare industry. Also, enhanced diagnostics. So if we had quantum sensors that are more precise, more sensitive, we could improve our diagnostic equipment. As well, improved medicine. And I get excited about this one, the virtual doctor and treatment plan. Like, I'm not like, I know, we're not there yet. And it's scary thinking about it from this point here, because I don't want a robot prescribing me medication or anything like that. But think to the future where all the bugs are worked out and you have an individualized care plan that factors in all of your health complexities, your genes, your things that you've inherited from your parents or whatever. And it factors in, oh, you had this health issue when you were younger, you have this health issue now. Here is your optimal care plan. And then data security. So healthcare data is the most expensive data that is sold on the black market. So if you want to talk about data that has a long lifespan that you would never ever want getting out into an adversary's hands, it's health data. Because if you have a general who has a peanut allergy, you don't want the enemies to know about that vulnerability. Okay, and then of course, travel, transportation, and logistics. So if we could use simulation to improve optimization to improve fuel efficiency, right? Maybe the routes could be optimized. Maybe you're the city of Calgary and every week you have to plow the roads 3 times and you want to do it as quickly and efficiently as possible. Perhaps quantum optimization could help with that. And then, of course, using quantum sensors, we could improve safety and navigation. And, of course, let's look at the finance industry. So using optimization, we could optimize financial portfolios and find the best way to get the greatest return with the least amount of risk. As well, in quantum communication, we could use quantum communication to improve authentication. So whenever we do a bank transaction, if you enter your credit card details there, you have to do an authentication, and that could be done using quantum systems. As well, if you're interested, there are publicly traded quantum companies that you can invest in right now. Okay? I'm not invested in any of them, but there are some amazing companies out there, and there are a ton, excuse me, there are a ton of startups as well, and lots of them are looking for cash. Oh, thank you. One sec, please. Yeah. One quantum second, thank you. Oh, I had a water right there. Okay, excellent. So the last industry we're going to look at, and perhaps the most applicable today, is municipal services. So these are some of the top areas that could benefit from quantum technologies, looking at multimodal transportation problems. So that's where you have goods or people, and you need to move them throughout the city using different modes of transportation: bus, train, car, bike. We had a bike in here yesterday that was used for delivering goods, right? Then there's waste collection, or same could be applied to snow removal, right? although there are different complexities in those problems. Emergency services could be improved. Maybe the response time for a 911 call could be improved by a couple of seconds. Maybe it could be more. I'm not sure. We'd have to explore it though. And then data security. So there is a lot of sensitive data that the city has that could be protected using post-quantum cryptography or exploring quantum key distribution. And as well, energy storage and distribution, as I mentioned at the start of my presentation. And Catania is going to talk more about energy storage and distribution. Okay, so let's talk about the opportunities now. So get engaged with quantum so that you can start taking advantage of these opportunities. So you could gain a competitive advantage, do something better than your rival. You could prepare for disruption because these technologies are coming and they are disruptive, so you might as well prepare for them now. As well, there's the added benefit of finding new solutions. When you engage in deep tech and you explore new solutions, it makes your business more agile. You're better prepared to adapt to a changing environment. And we all know that the speed of change is increasing, right? So being more agile is a huge benefit to exploring quantum tech. And finally, you could be viewed as a first mover. So sometimes that inherently has value for certain businesses to be like, I'm adopting quantum, and everybody goes, oh, they were the first to do quantum, whatever, and everybody wants to work with them then because they're the first mover. Okay, and then there are risks, as I mentioned before. So there's the risk of data security, right? That a fault-tolerant quantum computer could break current encryption standards. Does anybody remember what the timeline was that I gave on that one? Excellent. Thank you. 5 to 15 years. Exactly. So that means we don't have to worry about it until 15 years from now, right? All right, you guys are all paying attention. Excellent, yes. And why is that? What's that threat called? Yes, excellent. Harvest now, decrypt later. Awesome. And there's also a threat that your competition adopts quantum, right? Like Tokyo. Tokyo's already, they've been doing quantum for 10 years. I didn't know that. Catania taught me that this morning. So, you know, if we want to get Calgary up to speed, we need to adopt quantum to compete with other smart cities such as Tokyo. All right, and then of course, there's the disruption, as I mentioned. So disruption is when we change the standard way that businesses do operations. So when we introduce new technologies, it has ripple effects. So if you introduce a new technology, now the business behaves differently because of that technology. Either they integrate it or they mitigate it or whatever it may be. But disruption is real. It's going to come, so you might as well prepare now. I don't want to scare you too much, though. This isn't too much fear, right? We were talking about that on the panel. All right, so the flip side to this is beware of the hype. Make sure that you know about the current state and what's realistic in terms of quantum technologies. So as I mentioned, quantum is a new technology. It's a very nascent technology. It's just emerging now. So some of these wonderful, fantastical things that I talked about won't be available for maybe 5, 15, maybe 25 years. It depends. And also, quantum is not magic. As soon as we get a fault-tolerant quantum computer, we're not necessarily going to cure cancer, solve world hunger, reduce climate change, et cetera, et cetera, et cetera. It's not magic. It's an iterative process. It's a technology. It takes time to develop. And we heard some really good things, I feel like, on the panel and in the other presentations today too, that we're talking about how you've got to adopt this technology so that you can build your solution. What solution does your business or your business unit want to see? Because there's limited resources coming out of the quantum industry, and they're going to go to the highest bidder. So if you're not ready to bid on their services now, they're going to develop somebody else's solution, and that person is going to benefit from this, and you're going to potentially miss out. If you wait until it's already commercial and everybody is saying, yep, I'm on the quantum train, it's going to be too late. All right, and now let's look at the final section. So the investment in quantum. I always love showing numbers. Everybody understands numbers. So here's the overview. So in 2022, global quantum investment reached $2.35 billion. In 2023, it dropped slightly to $1.2 billion. That was more of a reflection of the investment industry in general. And from the looks of it, other industries saw reduced investments as well during 2023. However, don't worry, 2024 is up there already. Now, if you're wondering about Canada, what are we doing as a country? Yes, they do have a strategy, which is amazing. Way to go, Government of Canada. It is important to develop a strategy and prepare for this because of all of the issues that I just mentioned. Now, over the last about 12 years, the government has invested about $1 billion into the quantum industry, and they now have a national quantum strategy to invest $360 million over 7 years. Then by 2045, it's estimated that Canada's quantum industry will be more than $139 billion and account for more than 200,000 jobs. So it's a real industry, lots of money getting pumped into it, and real businesses. Now let's take a look a little bit further at some of the companies that have raised. So this year, earlier this year in April 2024, we have PsiQuantum. They raised close to $1 billion Aussie bucks, and the government of Australia invested in it. It caused kind of a stir because then it's like, hey, how come you invested in them? And should we invest in one company or should we spread it out equally amongst all the companies? But anyways, Australia, they bet on one horse. And that horse is PsiQuantum. They're a quantum computing company, and they're part of the Chicago Quantum Exchange. They are the backbone of the Chicago Quantum Exchange, which I think means that they're just providing the quantum hardware for the computer. They might be involved in other things though too, like networking. I'm not 100% sure, but I know they are quantum computing. Quantinuum, which is based in the US, they raised $300 million. And that is significant because that means that their valuation is $5 billion. Okay? So that means, you know, somebody invested a certain amount. They said, okay, I'll give you 300 million and I get X number of shares. That means that if you calculate, okay, multiply that by however many shares there are, that means the whole company is worth $5 billion. That is a unicorn. So if you have a company that's worth more than $1 billion, they call it a unicorn. We already have quantum unicorns. Then there's Pascal, which is based in France, and they raised 100 million euros, and that put them at a valuation of about 400 million euros. And then here, we've got Canada on the map again. So here we have Photonic Inc. They raised $100 million US. And then Sandbox AQ, they're based in California. They're a Google spinoff, actually. That's how they raised $500 million. Big money going into these companies. Real technologies are being commercialized. This is a real industry. So here is the world map. I've summarized it over here, but thanks to our friends at Curica, they released this world map just last week, so it is all current information. But if you see the top 5 countries, we have China. They've invested $15 billion into quantum tech. The US is just shy of $5 billion. The UK is $4.3 billion. And then Germany is $3.3 billion, and then France is $2.2 billion. Canada has invested $1.1 billion so far, and I'm not sure, but we've dropped a little bit in the rankings in terms of quantum investment. Okay, so I've given you all this information. Now, what can you do with it? Okay, great. Well, first of all, I want to mention you don't need a PhD in quantum physics to get engaged in quantum. You can start by creating a budget for quantum, even just a small one. Just get a small, you've got a training budget, so why don't you just dedicate like a little bit of that to quantum training and start preparing now so that the transition isn't so stark. Ways to engage, well, you could explore novel solutions. You could trial a proof of concept. And you could also develop a quantum strategy so that you know exactly what trigger events are going to mean to you and what you're going to do in action to those. And as luck would have it, Qubo Consulting offers these services as well. So if you're ready to start your quantum journey today, you can get involved with Qubo to discover quantum solutions. We have a 4-week program to get your team up to speed on the quantum industry, and we'll uncover problems and match with potential quantum case studies. You could trial quantum technologies. That's about a 3 to 6 month program to select a problem, identify appropriate quantum vendors, and start trialing a solution. If you're ready and the trial goes well, implementation. So if you want to deploy a quantum solution and prepare team members for the transition, that's one of our services. And finally, strategic foresight. So develop a quantum strategy and a roadmap to plot your course for capitalizing on opportunities and minimizing the risks of a post-quantum economy. We also offer training solutions. So thank you so much for your attention. I hope that you all learned a little bit about quantum today. Do we have any questions or comments or discussion? Yes, sir.
Okay, so I know that there's different types of quantum computers, like the superconducting one or the photonic ones and stuff like that. I'm pretty sure China is like leading the way with the photonic ones, and then in Canada there's Xanadu and stuff, and like there's one right there. But is there like a benefit to one over another?
That is an excellent question for our technical expert, Catania.
Thank you for your question. So yeah, there are like 10 to 15 different platforms. You can use atoms, ions, light. All these different quantum computers have different advantages and disadvantages, and it kind of depends on A, the application, and B, the hardware. So for example, a quantum computer made out of light can talk to other quantum computers made out of light really easily because the light can go between them. If you have a cloud of atoms, it's really hard to drive a truck of a cloud of atoms to the other cloud of atoms so they can talk to each other, right? So even if you have an atomic system, you might have then light to talk in between them. So all of this is kind of up in the air. We're still doing the R&D in this industry. There are a few front runners that are easier to do. So for example, we're really good at chip manufacturing, right? Like we know how to manufacture computer chips. And so the companies that know how to do silicon chips, they've just been going smaller and smaller and smaller with their circuitry and with their transistors. Eventually they got to the atomic scale and things started to not work right? Because you started to cross over into that quantum realm. So now they make superconducting circuits, right? So it's still the chip manufacturers, but now they're making circuits that work on the quantum scale, but you have to cryogenically cool them. So like I said, there's advantages and disadvantages to all the different platforms. And if you want to know more, we can talk later.
Yeah, I would just add, so yeah, definitely, if you have specific questions, and we would love to discuss further to match specific, yeah. Oh, yes, okay. So, like, I'm a very serious guy. I don't know if you got that from my presentation, but we have a quiz here that will test you on quantum. It's just a little quiz, okay? And no, I'm totally joking. It's just for fun. You'll see. You'll get there and you'll be like, AJ's hilarious. So you can scan the QR there and you can take the quiz. See, I think I got 93 and I thought there was something wrong with the quiz, but then Catania took it and she got 100. So we knew what the problem was. Yeah. I was, yeah, totally. You know what's funny? This was actually Colton, our marketing guy. He came up with the idea.
But AJ did make kids love math, and so now he's helping people love physics.
It's actually easier to make adults enjoy physics than it is to make junior high students enjoy math. Yes, Sandra.
Am I correct in what I heard that you mentioned quantum key distributions are theoretically secure? 100%. What would make them insecure or unsecure?
As much as I'd love to answer that, Catania is actually a domain expert on quantum key distribution, so I'll let her answer.
Thank you. And I've done hacking experiments on QKD systems. So the vulnerability is in the physical implementation of these devices. So when Alice and Bob, Alice has to send light to Bob to make the key. Alice has to make choices. Alice has to decide what bits to send. That has to be random. If there's any kind of, pattern to that randomness, that's a vulnerability. Same with Bob. Bob has to make choices. When Bob measures the signals, Bob has to make those choices randomly. If there's any pattern in that, that is a vulnerability. So there's a lot of vulnerabilities in like the randomness side of the choices. Then you've got the physical detectors. So we heard a little bit about that earlier this morning. The physical detector can be hacked as well. So there's a lot of these things, but that's why experimentalists like myself, we test these systems. We can actually find, can I hack it? Can I learn the secret key or something? Yeah. And I think based on the expressions, we've got some people trying this quiz, and it is funny, right?
Yeah. One word that I've kind of heard repeated over and over again, especially on the panel, was experimentation. And I think really like that's where you go from here. How do we move forward? We experiment. We try it out. We see what happens. We reiterate. We try it again. And I really like you saying that you're an experimentalist. That's what spurred my memory to think of that. But I think really like that's the action I should have put on the slide is experiment. One more question. I got time for one more question. Yes, sir.
So I suppose the quantum computer itself is a very advanced technology, so only a few top technology companies would have a working quantum computer. So like is everybody else who is working on it, they have some access to those computers and for their computing power?
Yeah, so what we're seeing typically is people offer like quantum computing as a service, and it's like a cloud-based access. And so it's not a full fault-tolerant functional quantum computer, it's a quantum processing system. So it can do some processing in a quantum state. And so what that means is all of the information that goes into it is actually on our classical computers. And so we have to input those parameters. And so that's kind of where it becomes a little bit complicated. How do you take these really big problems and you translate them from classical to quantum? But typically what they try to do is you get all the information, you get all the parameters, et cetera, and then you do the actual processing with the quantum system. And so it can be accessed via cloud. And there are different models as well because it's an economy, and so there's people who do this, there's people who do that, and so some people are actually trying to sell like physical computers to people. Like I've had people approach me on LinkedIn and they're like, "Hey, do you want to buy a 1 qubit computer?" And I'm like, "What the heck can you do with that?" Like, but they're for educational purposes, et cetera, and things like that. Yeah. All right. Thank you very much.
So Catania is really going to get into how do we really apply some of these quantum opportunities to solving some of our community's biggest problems. I'll pass it over to you.
Thank you very much, Jason. And thank you again to the City of Calgary and to Dave for having us at the WAVE Tech Center. We're very excited to be part of this. So hello, everyone. My name is Dr. Catania Kuntz. I'm an experimental quantum physicist. Today, I'm going to bring a little bit of quantum tech to your world. So in today's talk, we're going to start off with what is the second quantum revolution, because maybe you didn't even know that there was a first quantum revolution and we're into the second. I'm also going to describe our Young's double slit demonstration. That's just over there in the corner. It's demonstrating some of the very basic properties of quantum, and so I'm going to go through some of the key takeaways of that demo. And then we're going to get right into use cases. So we've got quantum computing use cases. We're going to talk about optimization and how that can be applied to a particular case study in Tokyo where they optimize the collection and transportation of waste. And then I'm going to go into quantum sensing. a lot of people don't know, but quantum sensors have been actually commercialized and available for over 10 years in some cases. So there's quite a few of applications of quantum sensors, and we're going to talk about the energy infrastructure and transportation infrastructure use cases. And I will define what is quantum LiDAR. And then finally, we will take action, because after you listen to all of that, I'm sure you're going to want to get involved, get started, get educated about what is quantum, and so I can help you with that too. So to start off, what is the second quantum revolution? Well, wait a second. What do you mean there's a second quantum revolution? I didn't even know there was a first quantum revolution. Well, all the devices that you're currently using right now to live stream and watch this presentation, electronics, the internet, solar cells that are powering your devices, these are all examples of quantum 1.0 technology. So this technology is based on the principles of quantum physics, but they're not operating at the individual atomic level. So for example, the discovery of semiconductors, transistors, I see there's pictures here of different types of chips and resistors. These are all devices that operate based on the principles of quantum physics. Other examples of quantum 1.0 technology, broadcasting technologies and wireless communication. So this is using different portions of the electromagnetic spectrum to transmit information. So we use radio waves, microwaves, optical light, infrared light to transmit information. Also GPS. GPS is a version of quantum 1.0. Each GPS satellite actually contains multiple atomic clocks to give you ultra precise timing. So that is a quantum device. X-rays, that's using a different part of the electromagnetic spectrum to examine your body. And even the LCD screen that you're looking at right now, this is all part of the quantum 1.0 tech. So now why are these examples of 1.0 and not 2.0? It's because they're all dealing with big signals, large samples, macro states, big. The behavior of atoms in the quantum world is very different to what we see in the everyday macro world. There's other principles such as superposition, entanglement, quantum tunneling. Now, if someone just randomly walked through the wall right now, I would be very surprised. But quantum tunneling is a real thing, and we use it in devices every day. Quantum 2.0 tech, right, is referring to using these quantum properties and materials like atoms, particles of light called photons, to do a task: computing, sensing, communication, random number generation. A lot of people often will talk about quantum computers, but there's other technologies too, such as sensing and communication. And this technology, you're addressing individual atoms. So, you know, smaller than the skin cells on your skin, smaller than the molecules, smaller than that. We're actually working on the atomic level, and we're measuring these signals. Also, you can send information using particles of light called photons, and this is called quantum key distribution. And I'm going to touch on that a little bit later. But these are examples of 2.0 technologies. So if there's no questions about what quantum tech is, I will go into our demo. So has anyone ever heard of Young's double slit experiment? Excellent. Yes, from high school, exactly. This was an experiment that I was introduced to also in high school. And I thought it was just fascinating then, and I'm still fascinated by it today. And it actually illustrates some of the really weirdness of quantum. So let's step through it together. And I'll use the mouse so that everybody online can see what I'm doing as well. Okay, so whenever you're looking at these types of diagrams, you always read it like it's a sentence. So you start on the left and you go to the right. And so we're going to start over here, and there's going to be this light source. So in our experiment, it's not quantum yet. This is just a light source. Literally, it could be a light bulb. Then you have a screen, and it has two holes in it, two slits. And that lets just a little bit of light through, as you can see. And then for this illustration, they've made one of the paths orange and the other path blue, just so that you can watch where the light goes and why. And so as the light's traveling, you can see that it spreads out right? Light spreads as it travels. Think of a flashlight. If I shine it to this wall very close, it's, you know, not too big. And then if I shine it way over there, it's huge. Light spreads. So as the light's traveling, it spreads, and then it starts to interfere. And so if you think of water waves crashing into each other, right? And when two waves add together, you get a very big wave. And when the two waves are perfectly out of sync, right? One's opposite of the other, like you see up here, then you would get flat line. You would get no wave, right? So that's constructive and destructive interference. So down here, you can see the waves are lined up, and then up here, they are perfectly out of sync. And so then what happens is the waves that are constructively interfering, the light waves, will make these bright lines in this interference pattern that you see on the screen. And the dark lines are from when the waves cancel, and it's destructive interference. And the demo that we've created does this with a laser. And when you take a picture of the screen, in the demo in this configuration where it's just two slits and that's it, you see this interference. You see this bright, dark, bright, dark, bright, dark. And if you'd like to see more, we've got the demo set up over there. And we also have a video looping to show you, because it's kind of not dark in here, so it's hard to see the laser. So we took some video in the dark. So now what happens if we actually watch to see which way the light goes? Which slit, which path does the light take? What if we were to watch? Well, this is the weirdness in quantum. The interference pattern disappears. So those lines that we would get before are now gone. Well, wait a second. Let's take a step back. What do you mean watch? Because I'm now using my eye, right, to look at this pattern that's being formed on the screen. So aren't I an observer? Like, what is this observer over here? You're right. The definition of an observer is taking a measurement, is observing something, right? So in this scenario, there's actually two observers. There is me, physically, looking at the experiment, yes, but there's another observer, checking which way did the light go, okay? So in terms of the screen and my eye, that observer, you're measuring it, you're measuring this pattern after the light has already traveled, right? It's not happening here, it's already happened, and you're taking a picture. That light is by measuring it after it's traveled through the double slit, it doesn't change the pattern. But if I watch which way the light goes, that changes the pattern. So this observer is the one that I'm focusing on, okay? So observing which path the light takes, it does change the pattern. And that is the very interesting part about quantum. So what's going on here? When there's no observer, when this is not here, the light just travels through, it interferes, and the reason why you're getting that interference is because you don't know which path the light took. So it's in a superposition state. I know that's a scary word, but it just means you don't know which one. Is it left or is it right? So it's in a 50-50 mixture superposition state. So by observing, we know the light went through there or it went through here. Just pretend in this thought experiment that you can literally watch this little slit and watch if the light goes through, okay? And if you do that, you've collapsed the superposition state. You know which way it went. So there's no interference because that interference was due to not knowing. So once that information became available, because you have an observer watching, right? Now that information of where did my light go is available, it changes the result. This is a very, very, very fundamental concept in quantum, that observation changes the result. Now, what would happen if I would turn this light source down, right? Instead of 1 billion trillion photons a second coming off the light bulb, what if it was 1 photon a second? So I was absolutely sure I was sending 1 photon, and these photons, they're indivisible particles of light, okay? They can't split in two. They can't just suddenly clone themselves and become 2 parties or something. It's 1 photon, and it has to make a choice. That one or that one. So if I was to do that, and I don't have the observer, okay, and we send in single photons, do you think you would still get the interference fringe? Do you think you would still see interference? Because remember, that was because we didn't know which way the photon went. So if there's no observer, do you think you'll see interference? Hands up if you think yes. Hands up if you think no. Oh, see, this is where quantum gets weird. You see it. You see the same patterns with single photons, even when you're sending in the light one photon at a time. It's mind-blowing. I learned this when I was 14, and I still don't believe it. But I've seen it with my own eyes, so I know it's true. You can actually build up these interference fringes one single photon at a time. Over time, as you saturate the camera, you'll see the lines. That's incredible, right? How could it be doing that? And then if you do observe, then it goes back to being no interference, just a bright patch of light. So single photons and a whole bunch of light act the same way. So what does that mean? Well, this is again what I mean by the weirdness of quantum. So the math and the experiment tells us it's as if the photon is traveling through both slits at the same time, interfering with itself on the other side to make these fringes. But like I said, a photon is an indivisible particle of light, so that's not possible. So somehow this interference is happening, right? And then when we watch, it goes away. So it's also as if the photon is acting as if it knows whether you're looking or not. Now, I know I'm personifying a photon. No, they do not have feelings. No, they do not make choices consciously. But the math is showing us that superposition, you don't know which way it went, you get interference. You know which way it went, you know the information, no interference. That is the main concept. And why is that so fundamental? I will link it to some of the quantum tech ideas that we will discuss next. So this is the actual physical demonstration. So before, we were just using our minds, right? We were just thought experiments. Let's pretend we can watch the light. Well, now we're going to actually do it. So no observer in the path. This piece of glass here that the arrow is pointing to, this piece of glass here for the observer, what that is, it's a wave plate. It's a special piece of glass that changes the polarization of the light that travels through it. And we're sneaky. We put that special piece of glass only covering one of the slits, so one of the paths. So when we put the observer in the path, you can see on the IR card that's showing the light, you still see the two lines that are from the double slit of the light traveling through the double slit. Just like when there's no observer below that, when there's no wave plate, you still see the two lines, right? But when there's no observer, you get the interference. But when there is an observer, you don't get interference. And so what's happening here is we're using polarization to create information, basically. If the light goes through the right slit, it's going to be one polarization. If it goes through the left one, it'll be a different polarization. So because we've made the two paths distinguishable, it collapses the superposition, and now we don't have interference. So without an observer, you get interference.
When you did polarization,
Yes.
so by doing polarization, you know which path it is going through. That's
Yes.
why you're doing the polarization.
Yes.
But then on top of that, if you don't have an observer,
Like my eye looking at the pattern?
or a camera, yeah.
Yeah, so then we start to cross into a little bit of philosophy. You know, like if I do the experiment, did it actually get done unless I look at the data, right? No.
At the end result, that
Yes.
doesn't matter.
Right.
That's not an observer. So
Yeah.
if you don't look at the time of the experiment, you're just doing the polarization.
Yeah.
So then does it matter whether you have an observer or not?
Well, the polarization is the observer. Yeah. Yes.
Okay, so if you're using polarization to determine which slit it went through,
Yes.
doesn't that mean your slits have to be like this? So
No.
You're distinguishing one from the other by the polarization?
Yeah, but the light can still travel through the slit. It doesn't have to be a certain orientation. Yeah. Excellent questions. I know, and this is baffling, and if you want to talk more, I'm here all day, and we're right there with the demo. Oh, good. So it's a mind-blowing demo, but what's the point, right? So the main takeaway is that the act of observation or measurement affects the quantum object being the atom, the photon, the light, whatever you're measuring, right? And so what are some examples of this quantum property in quantum tech? So the security of quantum communication, for example. So there's something called quantum key distribution, QKD. Now this is the real-time generation of an encryption key. And the encryption key is being generated between two parties, Alice and Bob, A to B, right? Sometimes scientists are not so imaginative, and so we just chose Alice to Bob. And Alice is the sender, Bob is the receiver, and they're using light to generate this key. Now, if a hacker, an eavesdropper, is trying to steal information, the eavesdropper has to literally steal a photon. And as I already said, photons are indivisible. You can't just steal half a photon or a little bit of a photon. You have to steal it all. That will affect the light because the eavesdropper has to make a measurement on that photon that affects the photon. And so then Alice and Bob would be able to detect the presence of somebody tampering with their light because it affects the light, just like you just saw, right? The interference went away when observer was present. Similar things happened in this case. So an eavesdropper cannot learn your secret key without disturbing the light. And that's one of the concepts that's key to that encryption being secure. Another concept that this demo is demonstrating is a quantum computer. The fact that a quantum computer is using qubits, quantum bits, and these exist in a superposition state. Remember I mentioned superposition? So your traditional classical computer doesn't do this, right? Its bits are either a 0 or a 1. It's not in between. If it was a 0.5, that would be counted as an error and it would be discarded. Whereas a quantum computer, it stores and processes the information differently. It can exist in a superposition state of 0 and 1. And the qubit will exist in that state until it is measured. Then it will be collapsed to one value. So these are very, very fundamental concepts in quantum tech, and the observer effect is part of this concept. So are there any other questions right now about the demo? Yeah?
The photon, so when you observe it, it's something like, could it be like changing from particle to wave? Because then you said superposition, that's what the wave does, even if you're just sending one photon. So is this part of the theory that it's something like
yes. Yes, so Young's double slit experiment talks about particle-wave duality. So the classical idea is that a wave will show you interference and that a particle will just go straight through and not have interference. That's the classical way to look at it, right?
If you look at it, then it behaves like a particle. And if you don't look at it, if you're not an observer, then it behaves like a wave.
Yes, and so the problem with this language is that a photon is a particle of light. It is a wave packet of light. It acts like a particle and it acts like a wave. And you can get these concepts and you can create, so for example, so interference, you usually think of it as terms of waves, but you can get interference fringes from single photons. So particles of light can have wave-like properties. So it's not so much does the object act like a wave or a particle, it's more do I have information about which way it went? Then do I get interference or no? If I don't have path information, I know which way, I don't know, interference. And if I have the information, no interference. But I know what you mean. Usually when people explain these types of experiments, they explain interference as terms of waves and no interference in terms of particles. But that's a little bit inaccurate because of the language. Okay. So now we'll get into some use cases. So when you're solving optimization problems, you don't need to have a full-fledged, fault-tolerant quantum computer. You can use other quantum systems, and one of those systems that you can use is called a quantum annealer. So this is a picture of a D-Wave system. It's a quantum annealer. It's a superconducting circuit. So a little bit earlier when we were answering some of the other questions, I mentioned how devices that, companies that make chips and wafers, silicon wafers, they also make superconducting circuits. Because as you can see, this is just basically a computer chip, but they've made the device even smaller. Also, because it's superconducting, it has to be housed in this special cryogenic cooler. So all of this cabling and things like that, it's all to get the signals in and out of that system, and then also cool it to almost 0 degrees Kelvin. So very, very, very cold. And how these annealers work is you take one of these circuits, and you can actually program your problem. So say you have a traveling salesman problem, you have a delivery route problem, things like this. Problems that are very difficult to solve with our current computers. You can code it into this circuit and then allow it to evolve over time. And because everything in the universe wants to be at its lowest energy state, right? Think of a ball rolling down a hill. It doesn't want to stay at the top, it wants to be at the bottom. Same with this device. You code in your problem, it evolves to its lowest energy state, and that is the solution to your problem. So D-Wave uses these quantum annealers to solve various optimization problems, which are also called NP-hard problems. And these are problems that get exponentially harder to solve every time a new parameter is added. So there's so many applications. I could have filled 5 slides with all the, with the list, but I just picked 4. Balancing financial portfolios, solving transportation and logistics problems, new drug discoveries, also manufacturing. So AJ touched on some of these already, but I just wanted to highlight that again. So again, this quantum processing unit, it's going to consider all the possibilities to solving this solution, solving this problem simultaneously, and then it finds the lowest energy that's required to form those relationships, and that's your solution. So it's literally using nature to do the computation. So let's look at a case study. So D-Wave worked with Grovernauts and Mitsubishi to combine machine learning and deep learning with a quantum annealer to try to optimize the collection and transportation of waste, and in Tokyo. So they were modeling all sorts of parameters, including the number of tenant companies and employees in each building, waste collection regulations, vehicle specifications for transport, for example, loading capacity, access and positioning of loading and unloading areas. Also the amounts, the collection routes, required labor time and collection frequency for each type of waste. The list of parameters goes on and on, right? And usually these are massive data sets that are fed into supercomputers that clunk along and try to come up with an optimized route for this solution. So all of that data was also combined with weather data and district event info as well, because that can change the traffic and the waste collection requirements. And they created a forecast using an AI model. So it's not just quantum, right? We always want to involve the best of the best tech, and we want to outsource the really hard problem to the quantum device, right? So AI was used to forecast the amount of type of waste that we generated over several months. And this future waste predictions actually had an accuracy of about 94%, which is very good. The AI prediction was used with quantum annealing to simulate a combination of routes and found optimized solutions that would require fewer vehicles and much shorter distances. So you can see the differences here. Even though the arrows are pointing up, these are actually differences down, right? So the current situation here, the total distance, number of trucks, 75 trucks. The working time is, a lot of minutes, almost 9,000 minutes. And once they ran the optimized quantum solution, the route distance was reduced to more than half. It's only 31 trucks now instead of 75, and reduced working time as well. So the other advantage to this is your CO2 emissions were also going to be reduced. They were reduced by 57%. So when someone asks me, how can quantum tech help climate change? That is a way. All right, so that was just a little taste of optimization. And now we're going to look at quantum sensing use cases. And there is quite a few, so this will be a little bit longer. So this is, quantum sensing is improving the sensitivity using quantum objects and properties. So when we do a measurement with a quantum sensor, you're going to have an enhanced sensitivity, better than what your current devices can do. And this is due to the quantum properties that you're going to harness, right? So maybe you're going to use entanglement. Maybe you're going to use quantum coherence. Maybe you're going to use photons and things like this. So a quantum sensor is leveraging the properties of atoms and light to improve the measurement. So here's some examples of properties that quantum sensors can detect. So gravity fields, magnetic and electric fields, single photons. So detectors that can actually detect single photons are quantum sensors. So for example, avalanche photodiodes or superconducting nanowire single photon detectors. You can do hidden object detection, and I'm going to talk about that more later. Time. You can have more precise atomic clocks. You can have individual portable GPS units that are not reliant on a satellite link. That's very important. Temperature. You can do temperature sensing even more accurately than current sensors. Also movement. There's accelerometers based on quantum sensors, and gas. So if you have volatile gas that you want to detect in your environment, and maybe it's in very minute quantities, a quantum sensor might be able to help you. These types of devices are being commercialized now and have several applications. So for example, medical imaging. So we could have a portable MRI. You could also improve image quality from a better sensor. Spectroscopy using for characterization of materials and chemicals. So spectroscopy is just the analysis, chemical analysis. Enhanced GPS, as I mentioned, and inertial navigation systems. So this could be portable, reliable timing sources. Detection of gas leaks, remote target detection, radar systems, quantum light detection and ranging, that's LiDAR, and we're going to talk about that in a minute. There's also other industries like the mining industry would be interested in detecting magnetic fields and gravity fields, and so there's a device called nitrogen vacancy centers, and these are quantum sensors commercially available right now. There's even companies in Canada like SB Quantum that are making these devices, and you can do 3D mapping with more precise magnetic fields than you can do with conventional sensors. And finally, components for quantum computing and communication. So I mentioned how there's different platforms for a quantum computer. So there's light, there's atoms. If you have a light-based computer, you need to measure it in order to find out the answer of your calculation. That is a detector, and that would be a single photon detector. You can also connect multiple quantum telescopes to improve resolution. So there's actually astronomical applications of these quantum sensors. And in particular, since we're in Alberta, let's talk about the energy sector. So quantum sensors could be applicable for renewable energy and nuclear waste management, fossil energy, geothermal energy, electricity delivery and reliability, vehicle electrification, and energy efficiency. So let's focus first on the energy infrastructure. Conventional sensors are limited in accuracy, sensitivity, resolution, how much coverage they have, their responsivity. These are all going to affect how efficient your building management is, for example. If you don't have the data, then how can you improve, right? Also, have you ever had that problem where you're sitting in your office or in a building and you have to start waving your hands in the air like you just don't care? Yeah, because your sensor is a passive infrared technology and it doesn't detect slow-moving occupants, or it struggles to detect occupants if there's obstructions. Conventional gas sensors also lack the sensitivity to detect low levels of volatile gases, which could be affecting your indoor quality. And the integration of renewable energy sources into the grid, that relies on accurate and timely data from sensors. So now we have wind, we have solar, we have water, there's so many different forms of electricity. All of these things need to be integrated into the grid, and the timing of those signals is incredibly important. And quantum sensing could help with that. Timing and phase. So I know this is a big chart and it's a little scary, but we're gonna step through it, and we're just gonna take a look at some of the quantum sensor technologies and then their applicable use cases below. So here we've got quantum sensors for temperature and gas. That could help with your comfort monitoring inside buildings, also your air heating and cooling management. You have quantum imaging. That could help with trying to find your occupants, right? Occupancy monitoring, also the heating cooling management. Then there's solar irradiance. That could help with renewable integration. There's also quantum voltage and frequency detectors. That could help with your power quality and your grid resilience. And finally, there's devices called quantum dots, and they could assist with energy storage and energy conservation or conversion. If you'd like to know more about any of these use cases or case studies, please come talk to us after. I'm gonna focus right now just on one. So for example, in the temperature and gas detection, temperature sensors that are based on single photon interferometers, interferometer meaning interference, right? So these single photon interferometers allow you to measure the temperature of inside buildings to a ridiculous degree. So for example, the sensitivity of one sensor, just one sensor, is 0.00115 degrees Celsius. That's the temperature difference that it can detect. Sensitivity is the smallest change in temperature that one sensor can detect. That's very, 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 very small. Now, take a whole bunch of sensors, have a mesh of sensors, right? Now that entire system is going to have a resolution. That resolution in this particular case, the journal article that I'm referencing here, was 0.029 degrees Celsius. Also, incredibly fine detailed resolution. And resolution is the smallest unit of change in temperature that the entire sensing system can detect, right? So even if one sensor can be very, very, very accurate, when you combine them all together, and now you've got to combine the data, maybe there's some electronics, maybe there's some noise, maybe there's some jitter, so it might affect your resolution overall, but it's still incredibly good compared to conventional sensors. I mean, my thermostat can only do 0.5 degrees, so this is already an order of magnitude smaller. And having these more localized and precise temperature readings in buildings can really help identify these areas of inefficiencies to help improve your energy usage monitoring and even support targeted fitting. So what about the transportation area? Again, big scary chart, but we've got all of our quantum sensor technology up at the top and then use cases down below. So I mentioned accelerometers, and there's also strain gauges. That could be very useful for transportation infrastructure monitoring, road condition monitoring, and freight weight. And then there's magnetometers and gravimeters. Those could help with traffic flow, signal time optimization, and dynamic traffic control. Quantum radar, cameras, and LiDAR. We'll talk about this a bit more. That helps with incident detection, incident investigation, and freight vehicle platooning. There's also quantum accelerometers and gyroscopes, and they could help with cargo conditions and transportation route optimizations. And then finally, we were talking about the gas and thermometers. So that could help with detecting if you're in your cabin, if the driver comfort is okay, and outdoor and cabin gas detection. So a mouthful. There's so many different applications, and this is just quantum sensors in one little industry. And remember, there's computing, there's communication, there's random number generation, so this is just one little area of quantum tech. So let's focus on quantum LiDAR. So what is quantum LiDAR? Well, what is LiDAR? So LiDAR is similar to radar. Radar is with radio waves. LiDAR is with visible light. And basically, you're sending a pulsed signal In this case, with classical LiDAR, it's just going to be a classical source, which means not single photons. It means a bright laser or pulse laser, something like that. And then that signal is sent towards your hidden object, right? And then that object will reflect some of the light, scatter some of the light back, and then you measure it. But in classical light, in this classical scheme, you can't tell the difference between the signal and the background. It gets smushed into one signal that you measure. And you can create a 3D map based on the time arrival difference between the sent and received light. So how far something is can tell you how long the light took to get to you, tells you how far away something is. So now, in the quantum sense of quantum LiDAR, we're going to replace the detector with a quantum sensor. So it's a single photon detector. This is going to give you a much higher resolution image compared to the conventional techniques. And these photonic quantum sensing properties, right, we're exploiting the quantum nature of light. So photons operating with light. And there's a range of applications. So in particular, we want to look at this target analysis. So now, in quantum LiDAR, the light source is a quantum source. And so it's entangled photon pairs. Entanglement just means special correlation, right? There's a special relationship between these pairs of photons, and they are entangled, in this case, correlated in time. So you can see on the image here, we have 2 spikes of data. These are the detection events that have been measured of the idler and signal photons. So that's the traditional names that people have given these particles. So when you have an entangled photon pair, one's called the idler, the other is called the signal. And because they're entangled in time, you can see on this graph that when I see a signal, I see an idler. They're always correlated. Now, the signal photons are going to be sent towards the hidden object, whereas the idler photons are actually going to be kept with the user and sent to your quantum LiDAR detector. And you'll find out why in just a second. Now, the detector is going to measure the signal photons that are coming off the hidden object as well as the background. However, what about the background? Is it correlated in time with the idler photons? No. No, because the background is random. And so we can use this to our advantage. And we can try to eliminate those detection events that are not correlated with our idler photons, because we know that they weren't our signal. They're just background noise. So this allows you to significantly improve your signal to noise ratio. And the distance information that you learn about the object can still be learned from the time delay observed between the signal and the idler photons. So you only pay attention to where you see this coincidence spike. And so this is extremely powerful because there's a lot of situations where you might have an obstruction in front of your hidden object, right? Like maybe it's foggy. Fog scatters normal radar, LiDAR beams. If you can cut through that fog, because even though your beam has been scattered, the signal that you do get is the signal that you want, that is a significant improvement. Okay, we did it. We got through the full lecture. We found out all about quantum sensing, and now I'm sure you're all ready to take action. Well, luckily, Qubo Consulting is here. As I said, we are consultants and trainers. So if you are interested in starting your quantum journey, please contact us. We have a quantum discovery solution program. It's roughly 4 weeks long. We go from what is quantum. We get your team up to speed on the relevant information for your organization. I'm not going to break out the textbook and start teaching you Quantum 101. It's more about targeted learning to see what is the potential of the quantum industry for you. Then once we've identified a problem that could be applicable with quantum, we can move on to the trial phase, which is roughly 3 to 6 months, where you can try a problem, identify appropriate quantum vendors So AJ and I are very well connected in the quantum industry. We'd be happy to help you learn and be introduced to these quantum vendors and start trialing a solution. Or maybe you've already figured out what you want to do and you want to now deploy something quantum in your industry. Well, we can help train your team to be quantum ready and quantum aware so that you can deploy your own quantum solution. And finally, there's strategic foresight, developing a quantum strategy and a roadmap to plot your course for capitalizing on opportunities and minimizing the risk of this post-quantum economy. So please go to our website. There's lots of free content, blogs, videos. We have a YouTube channel, and there's lots of things to see. Thank you again for your attention. Please link with me on LinkedIn if you're interested, and check out the website. Like I said, we're friendly people. We don't bite. And I'm sure all of you have now become at least 10 points smarter on the IQ scale in quantum. So please check it out and take our quiz. It's really fun. We've come up with some, fun questions. It's not all serious. It's a little bit of humor involved. And test your knowledge with our quiz. Thank you very much. I know we already answered a lot of questions during the talk, but are there any other questions? Yes.
I have a technical question.
Oh boy.
Yeah, I have a technical question, sorry. So if you have a quantum LiDAR that is sensing a hidden object, how do you encode those entangled pairs in time so that they arrive at the same time when one photon has to travel further than the other photon?
That is an excellent question. First, the entanglement in time is going to be generated by your source. So that's already made and you're done. You're right, the path to go from your source to the detector is very short for the idler photon compared to the signal photon that's going all the way to your hidden source and then back, right? The important thing is these devices are usually set on a clock. They have some sort of timing. And so even though there's that delay, you can then overlap and find those correlated time slots, and that's how you would get the data back. So yes, there would be a big jump, but then you can overlap it and still find those correlations. Yeah, excellent question. That's more in the minutia of how we actually do it. Yes.
You mentioned, Catania, that everything in the universe wants to be at its lowest energy state. How does frequency and vibration also affect that energy?
Excellent question. So right now, we are in the era of noisy qubits. That's what we call it, right? So a quantum computer, we use qubits, right? And the noise of the environment disturbs the system. So exactly what you're saying, right? So in the terms of like a superconducting circuit, for example, we want it to be super, super cold, lowest energy state. But then the heat of the room could increase its vibration, could warm it up. And then that would actually destroy the quantumness, and it would turn it from a quantum thing to a classical thing. So when we're dealing with vibrations and noise and frequencies and things like this and heat, we want to minimize it as much as possible because it will transition your quantum state to a classical state. Excellent question. Well, one more.
Thanks. I have another technical question. So how far in free space can you do a quantum LiDAR like that?
So with quantum LiDAR, you would need line of sight, basically. And so in terms of free space, as long as you've got line of sight and you can still pick up your signal, it's strong enough, then it should work. Yeah. So the curvature of the Earth? No, because the signal, yeah. So you have to have line of sight, but then it has to be close enough that you can still measure the signal. Because as I mentioned with the flashlight, light spreads, right? So if I shine a flashlight to this wall, it's gonna be maybe a foot big. And then if I shine it way over there, now it's like 3 feet big, right? So the light's gonna spread. So even if you're sending a signal from the Earth to the moon, it'll eventually get there. But when it finally gets there, it's gonna be very, very weak because it's spread so big. Like when we were doing the satellite experiments with the KeySat the quantum encryption and science satellite. We're going to send light from the ground that's only 8 inches in diameter. By the time it gets to the satellite, it's going to be several meters wide. Yeah. And that's the best that we can do. We're making our telescope to make it as what's called collimated, so the light is all parallel, so it doesn't spread as much as, you minimize the spread as much as possible, but it still spreads. So with the LiDAR, that's one of the limiting factors.
So how far is free space QKD possible? Is it still
The longest demonstrations in free space QKD that I'm aware of is like 50 to 100 kilometers, maybe. I would need to look it up. But again, that's the problem. Like after like 20, 30 kilometers, your atmosphere, when you're dealing with these experiments on the Earth, you have to send the light through the air. The air messes up your light. It absorbs some of the light, it scatters some of the light. So everything that gets lost destroys your signal. And so as long as you can still pick up your signal, then it's possible. Yeah. Good questions.
Oh, Anne. Hi. So you were mentioning a bit about transportation and everything like that, and it's all kind of land-based, but there's a lot of innovation happening in drone technology and airspace management. So I'm assuming there's a lot of interest in like quantum computing in relation to those areas. Have you heard a lot about how that's being leveraged?
Yes, definitely. There's a lot of talk for drones because these quantum devices are nice and light. They're small, they're compact. Usually they use less power to operate, things like this. It depends on which platform and which device, right? This isn't universal. But I'm saying there are devices that are being designed to be space ready and drone ready. And so I'm aware of drone demonstrations using quantum key distribution where they demonstrated quantum communication doing it. I'm not sure about optimization and things like that, but definitely for sensing. So you know when we currently have drones flying around the city doing all these LiDAR and measurements of the roads and things like that, that has been done, I believe, by other cities, by at least trials, where they put quantum sensors in there. So love to talk more about that. And wastewater management, wastewater and flood modeling. But that's not really drones. Yeah, it could help. It could help. But I know with Calgary, we're very interested in when the river might possibly flood again. And so that's a serious problem that's been studied by other institutions as well. And I'm aware of a use case in Vietnam where they modeled their floodplain and they were able to come up with optimized ways to find, okay, this is where it's safe, this is where it's not, this is the predictions for the future.
Cool. So we talked about the surf wave yesterday, I think it was. But so there's a surf wave. We actually have a wave that was downtown, and it was caused after the floods. And then what happens is that it caused a buildup of sand, and the silt is built into it, and the wave's gone. But there's a real push to mitigate that by putting in a man-made surf wave, and it would have a bladder that blows up, and then it would have a adjustable surf wave. It's really cool. But in Ottawa, they've built a room twice this size, and they've actually modeled the 10th Street Bridge and the river and everything there, and they're using quantum computing to look at all the different models of what's the best way to mitigate the floodplain and the silt buildup. And it turns out a surf wave, which would be super fun, looks to be the most effective way to reduce silt. But they're using those high compute modeling that can happen in a controlled environment. Okay. Thank you very much. Dave.